let's start this video with an example. So here is our example. Let's let fn of x, this function is the arctangent of n times x. And for those of you who have forgotten your inverse trig functions, the graph of f1, here is y equals arctangent of x. You may remember it has horizontal asymptotes at pi over 2 and negative pi over 2. And then if you take fn of x, multiplying by n on the inside, remember, is going to squeeze the function towards the middle, which in this case is going to make it look more and more like this. So then we're going to let f of x, we're going to need a piecewise defined function here. This is going to be 1 if x is positive. It's going to be minus 1 if x is negative, and it's going to be 0 if x is equal to 0. And then it should be pretty clear to you that each fn is positive, is continuous. The target function f is not continuous. If we draw that on the graph, that's this line, this dot here in the middle, and then this line, and we've got a jump discontinuity there in the middle at x equals 0. But nonetheless, you can see that fn is converging to f pointwise. So you can have a sequence of continuous functions that converge pointwise to a discontinuous function. So if the functions you start off with have a good behavior, their limit might not have that same good behavior. So the content of this next theorem that we're going to prove is that this can't happen with uniform continuity. So our theorem says we start out with a domain, and a function, a sequence of functions defined on our domain, and a target function defined on our domain. And as usual, and we're going to suppose that the following two things are true. So the first is that each fn we suppose is continuous. And the second thing we suppose is that fn converges to f, not pointwise, but uniformly. So fn converges to f. And then the conclusion is that then we can't be this arctan nx situation. The limit function, the uniform limit of continuous functions is also continuous. So let's prove this. And we're going to start out by writing out formally in terms of epsilons, n's, everything, all the things we have assumed. What does it mean for Fn to be continuous? What does it mean for Fn to converge uniformly to F? So we know that here's the first thing we know. If n is a natural number, if A is a point in our domain, and if epsilon is positive, then there is a delta. There is a positive number delta. And let's notice here what it depends on. It depends on all of those things. It might depend on n, implicitly on an Fn, but we'll just summarize that in saying it depends on n, it depends on A, it depends on epsilon, such that if x minus A is less than delta and x is in X, our domain, then continuity gives us that because Fn is continuous, Fn of x minus Fn of A is less than, let's write down an epsilon. We might discover later in the proof that we're going to want an epsilon over 7 or an epsilon squared or something. Very common in analysis, you need a smaller value of epsilon. So that's the precise epsilon delta characterization of continuity. And loosely, this is saying that if x and A are close to each other, then Fn of x and Fn of A are also close to each other. So what's the other thing we know? We know that Fn converges uniformly to F. So we can write this as, for any positive number epsilon, there is a number capital N, a natural number capital N. And what does that depend on? That depends only on epsilon. Well, it depends on epsilon and the whole FNF system, but it doesn't depend on a particular N or X. So depending on epsilon and nothing else within the constraints of the problem, such that if x is a point in our domain and n is a natural number that's bigger than capital N, then Fn of x minus f of x is less than epsilon. So we see we can make Fn of x minus Fn of A and Fn of x minus f of x, and presumably Fn of A minus f of A. We could make any of those small. So now, what is it we want to do? So here is some scratch work. You would not write this up in a formal proof for journal publication. You wouldn't write this up in your homework. But this is what we want to show is true. So this is some hints to ourselves. We want to say that f is continuous at A. So we want so put that in terms of epsilons and deltas. If A is in our domain and epsilon is a positive real number, then there is a positive number delta, also allowed to depend on A and epsilon, and such that if x is a point in our domain and A minus x is less than delta, then f of x minus f of A is less than epsilon. So we want f of x minus f of A to be small. That's what it means for f to be continuous. So f of x minus f of A. What is that equal to? What that is equal to, we're going to write a long chain of things that we know are small. We don't know that f of x and f of A are close to each other, but we do know that f of x is close to fn of x. And we do know that fn of x, we know fn is continuous. We assumed fn is continuous. We're trying to show that f is continuous, so we know that fn of x minus fn of A, that is also small. And then we know that fn of A is going to be close to f of A. That's from the uniform continuity. And then let's think about this for a moment. We can make this piece and this piece, we can make small by making n large enough. We'll make each of these pieces less than, say, epsilon over 3, and that depends how large we have to make n depends only on epsilon. In particular, we don't have how big we have to make n. It doesn't depend on A or it doesn't depend on x. And that's crucial. This proof can't work if you've got non-uniform convergence. But we saw an example before, so we really want to come up with a proof that only works for uniform convergence. So this is where we're going to use the uniform convergence by making these two pieces that I've highlighted in yellow small, by making n large enough. And then this middle piece here, we can make this small by making x minus A small enough where how small we have to make delta. Delta depends on, what does delta depend on? It depends on A, on n, and on epsilon. And the big point of all this stuff I've been writing out is that I want to emphasize we're going to pick n first to make the two yellow terms small, and then we will pick delta depending on n to make the blue terms small. So now let's write out the formal proof here, the part that would show up in your homework. So we start by instructing our reader to choose a point in our domain and a positive number epsilon. We're trying to show that f is continuous at this point A. The reader is chosen using the epsilon delta definition of limit. And we're using this epsilon to do that. And then we're going to pick a little n. Which n do we pick? It's the n that makes those terms in yellow small. So by definition, of uniform convergence, we have that there exists a natural number n such that we're going to write it this way: fn of x minus f of x is less than epsilon over 3 for all x in our domain X. If you want, you can go back to your original statement of the definition of uniform convergence and put an epsilon over 3 in it, or you can leave it, it's just an epsilon. It doesn't matter too much. We're just using the definition of uniform convergence with a slightly different value of epsilon. I suppose we will probably want to put an over 3 up here too in our definition of continuity. The other thing I want to emphasize is that uniform convergence means there's a capital N such that for all little n bigger than capital N, this difference is less than epsilon over 3, but it's quite common in analysis. We only really need one n. We don't need all the n's, so I'm only going to write down for one n. And it's sort of implicit in the proof that our n only depends on epsilon. It doesn't depend on x. And now, because once we've picked our n, because fn is continuous at A, we know that by the epsilon delta characterization of continuity, and I'm not going to make you write out by which theorem 1.7.5 will stipulate that at this point we know the epsilon delta characterization of continuity, that it's obvious there is a delta that is positive such that if x is in our domain and x is within delta units of A, then fn of x minus fn of A is less than delta. And notice that in our formal write-up, we don't have to do a whole lot of reminding the reader that delta depends on n and A, but n only depends on epsilon. That all of the keeping track of what depends on what we did up in our scratch work, that was to tell us what order we have to do things in. Then by the triangle inequality, if x is a point in our domain, then we'll write it out. F of x minus f of a. We need x to be in our domain, so these are defined. That's less than or equal to f of x minus fn of x plus fn of x minus fn of a plus fn of a minus f of a. This is the triangle inequality in the real numbers. We proved it at the very end of section 1.2 last semester. And then we observe that this is less than epsilon over 3. And then fn of x minus fn of a. And then another epsilon over 3. That's because fn converges uniformly to f, so we can bound fn of a. That was this condition up here. And we'll write that as by definition of n. And then we note that if x minus a is less than delta and x is in our domain x, then our middle term fn of x minus fn of a, that's less than epsilon over 3. So f of x minus f of a is less than epsilon. And we observe that scattered throughout this proof, we've got that there exists a positive delta such that if x is in x and x minus a is less than delta, then f of x minus f of a is less than epsilon. And so therefore that means that f is continuous at a, and because a was arbitrary, meaning we just picked one of the points in the domain, all we assumed was that a was in the domain. We haven't assumed anything special about it. F is continuous on the entire domain X. And that completes the proof. Now let's talk about theorem 4.1.8. This is pretty similar to theorem 4.1 and 0.6. The difference is that your functions, your fn's, they are supposed to be uniformly continuous. And the conclusion is that your target function, your limit function f, is also uniformly continuous. Now, don't get confused here. We're using the word uniformly twice, once for continuity and once for convergence. They technically mean different things, but they're related concepts. So just be careful in this proof. We've got the word uniformly happening, showing up an awful lot. And the way we tweak the proof for theorem 4.1.6 to make this work. So you start by picking your positive number epsilon. You don't pick your number a at the start. And then you pick your little n by the definition of uniform convergence. That's just coming from uniform convergence, not from the continuity or uniform continuity, so we don't have to tweak that first part of the proof. Now, then we replace continuous at A by uniformly continuous. Such that if, and then there's now a delta greater than 0, such that if the two numbers a and x are both in x, and x minus a is less than delta, then fn minus fa is less than delta. Remember, this is the definition of uniform convergence we saw last semester. It's that if you've got continuity from theorem 1.7.5 for every epsilon and every a and x, there is a delta such that if x minus a is less than delta, then fn of x minus fn of a is less than epsilon. Uniform continuity is that one delta is going to work for all the a's and x's. And then this is all we have to change to get uniform continuity. Is that this? We're going to finish section 2.1 by talking about how uniform continuity interacts with integration and differentiation. Uniform convergence. So I thought I'd start with an example showing how integration and regular pointwise convergence might not work well with each other. So let's start with this example. We're going to let fn be the function. I could write down a piecewise definition of this for you, but I don't think it would be very useful. Instead, I will just define it, say it's the function with this graph. Then, so here is the point 1 over n. Here is the point 1 over 2n. And then our function is going to be piecewise linear like that with a peak at 2n. Then notice as n gets bigger and bigger, this peak is getting skinnier and skinnier. So we have that fn converges to 0 pointwise. But not uniformly. And then we've got that the integral from 0 to 1 of fn equals 1 for all n. But fn goes to 0 and the integral from 0 to 1 of 0 is not 1, it is in fact 0. So pointwise limits do not play nicely with integration The integral of the limit might be different from the limit of the integral. And the content of our next theorem is that this cannot happen with uniform continuity. Let's we don't have a regular domain this time, an arbitrary domain. In this case, we're going to be looking at a closed bounded integral interval. We've got functions fn of and f. They're both defined on our closed bounded interval. And let's suppose, well, as usual, fn is converging to f uniformly on this interval. And we're going to say that each fn is Riemann integrable on AB. And the conclusion is that f is Riemann integrable on AB. And not only does the limit of the integrals, we don't even have to assume the limit exists, that it exists comes from our uniform continuity, and the limit of the integrals is indeed the integral of the limit. Let's prove this. Now, to prove this, we're going to use a claim that we could have proven back in section 3.1. As it happens, we didn't, but this is just something we want to state about upper and lower Riemann sums. Let's let G and H be functions whose domain is our interval from AB and whose ranges are, and we're going to suppose that they are both bounded. And if P is a partition of AB, and since you've had all of Christmas break to forget this, a partition, remember, it's a set of points between A and B. The smallest one is A. We label them X0, X1, X2 in order. And you can have arbitrarily many of them, so we stop at Xn. The biggest one has to be B, is a partition. Of AB. Then the upper sum of H over our partition P, that's less than or equal to the upper sum of G over our partition P. And then we add to that the length of our interval times the biggest in our interval that H minus G ever gets. And there's a similar statement for the lower sum of H, that's at least the lower sum of G. And then you can either add an infimum or subtract a supremum. I'm going to subtract a supremum. So this is what we're claiming is true for all partitions. And the proof of the claim is not too bad. Let's write this out for just the lower sum. The upper sum is pretty similar and a little bit, it's simpler. We remember that the lower sum, that by definition is you take the length of each of your intervals that you've broken your a minus b into, and then you take the smallest in that interval that h gets. And now let's notice that h of x is equal to equal to g of x, and then we add to that h of x minus g of x. And now if we specify that if x is in xj minus 1, xj, which is, notice, is a subset of the interval from a to b, then this g of x, that's at least the infimum xj minus 1, xj of g, and then this h of x minus g of x, that has to be at least the infimum over, in this case, let's go ahead and take the whole interval, h minus g. And you may recall from last semester, the infimum of a function is negative the supremum of negative that function. So we keep our first infimum the same. And then we get a minus a supremum. And then we have to flip the sign inside as well. And then, so the conclusion is that L of HP, that is the sum from j equals 1 up to n xj minus 1, that is greater than or equal to this times, and then we put the infimum of g minus the supremum of g minus h. We just break up the sum and then we see we've got this one piece that's got the infimum of g in it, and then this second piece notice that our supremum of g minus h, we can go ahead and pull that out of the sum. And then we're left with just the lower sum of g over our partition P. And then if you think about your sum for a moment, it's a telescoping sum. So we get just a b minus a, and then the supremum over ab, g minus h. And the argument for the upper sum is similar, so I will not drag us through that. Now we can get back to the main part of the proof. We have two pieces. We need to prove that f is integrable and that the limit of the integrals is the integral of the limit. So here's the first part. We're going to pick a positive number epsilon. And let's let little n be such that fn of x minus f of x is less than epsilon over 3 times b minus a for all x in the interval from a to b. And For this part of the proof, we're not going to need a big N and a little n, such that for all little n bigger than big N, we just need one n that this works for. We will use the big N, little n thing in the second part of the proof. All right. And then we're going to let P be a partition of AB such that we've picked our Fn, so now we can pick P based on Fn. The upper sum of Fn over P minus the lower sum of Fn over P. We want that to be less than epsilon over 3. And we remember that P exists by our favorite proposition for showing that things are Riemann integrable. That is proposition 3.1.4 from last semester. All right, and then we write the upper sum of F over P minus the lower sum of F over P. That's the upper sum of F over P minus the upper sum of Fn over P. And then we add to that the upper sum of Fn minus the lower sum of Fn. And then we add to that the lower sum of Fn minus the lower sum of F. All right. And then the upper sum of F over P. We're going to use our claim with H being F and G being Fn. And remember, absolute value of Fn minus F is less than epsilon. So this Fn minus F, it's less than, what was it, epsilon over 3b minus A. So this is at most upper sum Fn over P plus b minus A, then an epsilon over 3b minus A. It simplifies down to an epsilon over 3. And similarly, the lower sum of F over P, that's greater than or equal to the lower sum of Fn over P minus the supreme of F minus Fn. So that's again going to be minus epsilon over 3. So the upper sum of F over P minus the lower sum of F over P, that's going to be less than epsilon over 3 plus epsilon over 3 plus epsilon over 3 is epsilon. And so, again, by proposition 3.1.4 going in the other direction, 3.1.4 is an if and only if statement. F is Riemann integrable. To look at the other part, that is the now we're going to look at the other part, that is the limiting part. So now we're going to pick an epsilon greater than 0. And this is not going to be the epsilon in proposition 3.1.4. It's going to be the epsilon in proposition 1.3.3. It's the epsilon in the definition of convergence, not in proposition 3.1.4. And now we let n be such that if little n is bigger than big N, and in this case we need the two different n's again, then uniform convergence means for all x in AB, we have f little n of x minus f of x is less than epsilon over, let's just use plain old b minus a. Then we're going to let P be a partition. And then the lower sum of Fn over this partition P, that is less than or equal to, by our claim, the lower sum of F over P, and then we move the supremum to the other side. So supremum over AB of, let's see, Fn minus F, and that's less than or equal to the lower sum. Sorry, I forgot to multiply by b minus a. Let's go back and put a 2 up here, just because when you take the supremum of things that are less than epsilon over b minus a, you might end up, the supremum might be epsilon over b minus a, so I want this to end up strictly less than. Epsilon. Strictly less than epsilon, less than or equal to epsilon over 2, so strictly less than epsilon. And then we can certainly take the supremum over all the partitions P. Let's use a different letter since P was our particular partition. Then we'll make it just regular epsilon, which will give us a nice strict inequality. And then we remember that that supremum is the integral from A to B of f. And we've got an epsilon. Then we use the definition again, and we can write that the integral of Fn is the supremum of the lower sums of Fn over any partition P. Remember your Riemann integrable if the supremum of the lower sums is the same as the infimum of the upper sums. And so the integral of Fn is less than the integral of f plus epsilon. And then similarly, you can get an argument that goes the other way. So if little n is bigger than the big N we picked before, then the distance from the integral of f to the integral of Fn is less than epsilon. So that means that the limit as n goes to infinity, integral of fn is equal to the integral of f. And that completes the proof.